Hi and welcome to this tutorial on Schrodinger's wave equation. In this tutorial we're just going to have a look at the wave function. I'll spend a lot of time on the wave function trying to explain exactly what the wave function is in this tutorial. In the second part of the tutorial we'll have a look at Schrodinger's wave equation for the energy of each energy level, if you will, of an electron in an atom. The idea is not to be able to derive Schrodinger's wave equation, although there are many tutorials out there that can do that. I'm hoping to be able to explain what the wave function itself means. It's about explaining the wave-particle duality of matter. Okay, so let's have a look at the Schrodinger wave equation. Now, Schrodinger wave equation is just basically the conservation of energy, and if I just point that out to you, we've got the total energy of our system that we want to calculate. It can be broken up into its kinetic energy and its potential energy. So this bit here represents kinetic energy, and this is potential energy. You'll often see this written with a V or a U to represent a potential energy. In chemistry, it's often written with a V. And this is just the total energy. But we've also got this funny symbol here, which is psi, and that's a Greek letter psi. And a few maybe familiar constants here. We've got one constant actually, which is the reduced Planck constant, or h bar or h cross, and that is just really h over 2 pi. And there's the mass of the particle that we're interested in. This function here, psi, is what the tutorial's about really. It's about the wave function and how we represent particles as waves, and use these quantum mechanical equations to actually predict, in this case, the energy of the system that we're interested in, or the particle, at any moment in time and space, within reason. Okay, so this equation can be derived, and we'll derive it later on. The essence of this tutorial is not to derive this equation. I'll stress that, because there are so many tutorials out there, and videos and in notebooks and stuff like that, which will show you how to derive this equation and then not tell you what it means. So I'm hoping to give you some insight into what these terms mean and how powerful this equation is going forward. So let's have a look at this symbol here, psi. So this is a wave function or wave vector. Now psi, for what we're interested in, is we're just going to be interested in one dimension, so we'll just choose the x dimension. And if we look at it as a function of its position and time, then it can be expressed using this equation. Psi equals e to the I kx, where x is its position, put it in brackets because it gets quite long, minus omega t. You don't need to remember all of this, plus a symbol that looks like psi, but it's called phi. It's another Greek letter, phi. Just delete that. Okay. So it looks quite complex, but this is the wave vector equation, or the wave function, if you will, that we're interested in. And I'll break it into its component parts now. So k, symbol k here, just means 2 pi over lambda. In this particular example, it's just the symbol we're going to use to represent the wavelength. And that's in there because we've got a multiplication of k with its position. So we look at a sine wave, or a cosine wave is probably best actually. So we'll start off. So cosine, when the position is 0, has a value of +1, and it oscillates between +1 and -1. So we can do this. Not very good at drawing sine waves. Okay, so it oscillates between +1 and -1, and the position of the next peak, or crest, if you will, is by definition the wavelength of the particle, or whatever we're interested in, of the wave. So that's the wavelength. Now you can take wavelengths from trough to trough if you wanted to. But this position here is 2 pi. So it's gone through one complete cycle. So 2 pi radians is a complete cycle of a circle. So we use this value k equals 2 pi over lambda because if you consider this axis to be x, the distance away from the origin, if you look here, e to the I kx, we multiply, so kx will become equals 2 pi x over lambda. This is really a way of normalizing the whole system so that it's always going to be a function of the wavelength. So if we go 2 pi out away from the origin, x equals lambda in that case, and when lambda equals lambda, these two cancel out, and kx equals 2 pi, and as you'll see in a second, cos of 2 pi equals plus 1. So this equation actually will give you a cosine wave in that respect. So if I just move these out of the way, move these down to the bottom. If we look at this equation and expand it, this is actually what's called Euler's formula. Oh, I do like Euler's formula. It's one of my favourite formulas in the whole wide world. And Euler's formula basically takes e to the I alpha x and it can be expanded into a real and imaginary function of cos alpha x plus I sine alpha x. Okay, so this bit here is the real part, this bit here is the real part, and this bit here is the imaginary part. And by imaginary it just means it's multiplied by the square root of minus 1, which is I. So this is called Euler's formula, and as you can see straight away, this has that kind of form, if you will. So e to the I kx is very similar to e to the I alpha x. In fact, it's just a replacement. We've replaced alpha that comes with k. So you can see straight away that this psi, the wave function here, has some wave characteristics because this will vary as a function of cosine and a sine wave. Now the best way of thinking about this, I won't go into too much detail, is that they're probably just different axes. That's the best way to look at it. So imagine the cosines on the y-axis and the I sine x is on the x-axis. So they're like orthogonal or 90 degrees representations of the wave. And so a combination of those two will give you the two-dimensional wave that this represents. But I didn't want to go into too much detail of that because it's not really the point of this tutorial. So straight away you can see that this has got some kind of sinusoidal function, and that's where k comes in. And I brought this up, really I went into a little bit more detail here because this equation we'll use in a second to derive Schrodinger's wave equation. Also, it's important to see that this function here, psi, this wave function that everyone will talk about in class, so you do this in undergraduate physical chemistry in the first year, or maybe in first year physics degree, or maybe your teachers might talk about it at the latter end of your A-level studies. Now psi really represents the amplitude of a wave. So if we think about waves at a seaside, it's a very classical approach, then the waves at the seaside will have some wave function just like this that will tell us about the wave properties. So this bit here will tell us about the amplitude and position of the wave at a moment in time, just like we have it as on the sine and cosine waves. If we know the value of x, we can actually find out how high it is on this curve. This function here tells us about the oscillatory nature of the wave and how it's moving. So this one would be if it's moving forward. So in a moment in time, what would it look like? So imagine a ripple on a pond, and that's what this will represent. And this bit here is the phase of the wave, and this really represents, if you will, how two waves can get in sync with each other. So imagine, like I said, the sine and the cosine wave were 90 degrees out to each other, and this would be, if we had another wave interacting with that, what's the relative position of that wave to the other waves. So we don't really need to go into that because that gets really tricky. We're not going to look at this because we're going to use a wave that's not moving. and we're just going to look at the one-dimensional effects. So this derivation now is going to look at the time-independent Schrodinger wave equation. So we don't need to worry about t now. So in essence, what we're going to describe is psi, which will represent the amplitude of the wave, or how the wave function disturbs the water, in the case of a water wave and stuff like that. What's its contribution to the disturbance from the norm, if you will. Okay, so that's what wave functions are for. So we will use wave functions. I am going to start this tutorial on derivation in a second, but just to, if you're not too clear on why we use wave functions, if we think about the electron moving around the atom, and you've probably seen this many times in classical mechanics or classical physics approach to the interpretation of two charges would mean that this orbiting electron would lose energy and therefore spiral, because it's moving, would emit radiation and therefore lose energy and spiral into the nucleus, where it'd probably form a neutron under immense pressures and stuff. So we don't all exist as neutrons. We actually know that electrons orbit in shells, and we can do this quite easily in class using spectroscopy to have a look at the spectral lines of elements and stuff like that. So we know that there is some kind of quantization, if you will. They can only occupy certain energy levels. So we know that exists, and this actually takes that into account. So if you think about a cannonball being fired from a cannon, in classical mechanics you can work out the trajectory of that cannonball at any moment in time. So it'll be here after 2 seconds, it'll be here after 5 seconds, and after 10 seconds hit the ground or something like that. Well, that's all the wave function does. It's a way of predicting either the energy or the momentum or the position of a particle at any moment in time, as it's being described by a wave rather than a particle. So in the Schrodinger equation I've got here at the top, we're interested in the energy. Now that's another thing you probably won't come across, is that we can apply a wave function to different, this thing here is called the operator, and operates on this function here, what we call an eigenfunction, and this will give us an eigen function back, if you will, plus what we call an eigenvalue, this bit here, and that value is what we're interested in. So we want to find out the energy of the wave function at a certain time, moment in time, or position, or whatever, and this will give